Good evening, ladies and gentlemen, and welcome, and what a delight it is to see such a full house. This is technically an ordinary meeting of the Royal Society of Edinburgh. As you probably know, the Royal Society of Edinburgh is Scotland's academy. We have about 1,600 fellows covering all areas of academia, arts, humanities, social sciences, engineering, and also business, the arts, in the sense of arts practitioners, people from the civil service, from all walks of life. This lecture will be audio recorded, and an edited version will be on the Royal Society of Edinburgh website in a couple of weeks, something like that. This is an ordinary meeting, but there is no society business other than the presentations and the lecture. The minutes of the last meeting and the list of recently deceased fellows is available outside in the hall for those who want that information. I'm going to be presenting medals to 3 people, and then we will have the award lecture from Professor Padgett. And that will be the substantial part of this evening's business. So, to move to the presentation of medals, we start with early career prizes in the physical sciences. And these prizes, these medals, are named after Sir Thomas MacDougall Brisbane. Of course, you all know all about him, but I didn't, so I've got a little briefing. So, Sir Thomas MacDougall Brisbane was the 4th president of the Royal Society of Edinburgh. He held office for 28 years, God help him. He was a British soldier, a colonial governor, and an astronomer. He was born near Largs in Ayrshire in 1773. Largs will feature again in a minute. Educated in astronomy and mathematics at the University of Edinburgh, joined the British Army and had a distinguished career in Flanders, the West Indies, Spain and North America. He served under the Duke of Wellington and was promoted to Major General. On the recommendation of Wellington, Brisbane was appointed Governor of New South Wales, Australia, a post he held until 1825. And while governor, he tackled many of the problems that were arising through a rapidly growing and expanding colony. He worked to improve the land grant system and to reform the currency. And both the city of Brisbane and the river on which it stands, also called Brisbane, are named after him. So the Early Career Prize in Physical Sciences, the FRSE Sir Thomas MacDougall Brisbane Medal for 2014, is jointly awarded to 2 people, and I will call them up separately. First of all, Dr. Catherine Kazin from the School of Chemistry at the University of St Andrews, in recognition of her outstanding research and entrepreneurialism that intersects the human-computer interaction. So, Dr. Kazin, would you like to come forward and receive your medal? And the other awardee is Dr. Per Ola Christensen, also from the University of St Andrews, but this time the School of Computer Science, and now a lecturer in Cambridge and an honorary reader in St Andrews. And this is in recognition of his outstanding researchship and entrepreneurialism that intersects the human-computer interaction, in this case, artificial intelligence and machine learning. So, Dr. Christensen, would you like to come forward and receive your medal? And I'm pleased to say that both awardees are members of the Young Academy, which is great. The third prize we're awarding is the senior prize, which is known as the Lord Kelvin Prize Medal. Kelvin is another name that's probably quite well known to you, but again I have just a little bit of the backstory about Kelvin. He was born in Belfast, where many great people in 1824, and started schooling there, but the family moved to Glasgow when he was about age 10. At the University of Glasgow, as a professional scientist, he worked on the formulation of the first and second laws of thermodynamics. He did much to unify the emerging discipline of physics into its modern form, but he also had a career as an electric telegraph engineer and inventor. This propelled him into the public eye, particularly his involvement with the transatlantic telegraph project. He's widely known for realizing that there's a lower limit to temperature, absolute zero, we now call it, and absolute temperatures are now stated in kelvins from absolute zero in his honour. He was knighted by Queen Victoria. Having started life as William Thompson, he then became Baron Kelvin of Largs, or more usefully known as Lord Kelvin. He was the first UK scientist to be elevated to the House of Lords. He was Professor of Natural Philosophy in Glasgow for 50 years and refused to move from there in spite of very attractive offers from other prestigious places, and died at his home in Largs. And as you're probably aware, the awardee this year is Professor Miles Padgett of Department of Natural Philosophy, Chair of Natural Philosophy, and Vice President Research in the University of Glasgow. I've got so many pages I've lost my way. Thank you. So Miles Padgett is awarded the 2014 Lord Kelvin Senior Prize Medal for his outstanding contribution to the field of optics, his promotion of a global community of researchers in this field, and his commitment to the public engagement of science. And could I ask Miles Padgett to come forward, please, to receive his Lord Kelvin Medal. We're then very shortly going to proceed to the lecture from Miles Padgett. If you're interested in events at the Royal Society of Edinburgh, you can find a little booklet like this outside on the circular table. This gives you the upcoming programme. It runs to the end of December, and there'll be fresh editions for 2016. So could I now invite Miles Padgett, Professor Miles Padgett, to give his lecture, Lord Kelvin lecture. Thank you very much.
Thank you very much. Well, thank you all for coming tonight to listen to this, and thank you very much, Jocelyn, for this medal, which if anyone wants to look at it later, just come and grab me, and I'll be delighted to show them. I should say my first panic is over. You always, when you look at that blank screen, you think, my goodness, I hope when I get up there, I press a magic button, my screen will come live. So thank you very much for the audio visual.
Excuse me, some of us rely on the hearing loop.
Oh, righto.
If you stand away from it, we can't hear.
Thank you very much for pointing that out to me. So I'm very sorry. I'm very sorry about that. I will be. If you see me stray from this lectern, just gesticulate wildly, and I will promise you I will move back, at least in the direction of the microphone. So thank you very much for pointing that out. I should say it's a particular pleasure for me to stand here, because I was just telling the President a few moments ago, actually, my whole academic career was kick-started by the Royal Society of Edinburgh through their research fellowship programme. So when I'm 52 years old now, and when I was 28, 29, I can't remember exactly, I was fortunate enough to be given that opportunity by the Royal Society of Edinburgh to start an independent academic career. And if I may just say, just don't worry, it's not going to become a political speech. You know, we often beat ourselves up in the UK about doing things badly when it comes to the way we fund science. And yes, if I had a magic wand, I would do things differently. But one of the things that I think we should be proud of here in the UK is the opportunity that we, not just the Royal Society of Edinburgh, but other funding agencies too, give to our emerging scientists to actually become independent thinkers at a really young age compared to many of our competitors. So thank you, Jocelyn, on behalf, I thank the Society, I thank the President, I'm not quite sure what the right combination is, but thank you very much. Right, having said that, we're now going to get into the normal lecture mode, and what I'm going to try and introduce us to this evening is essentially a topic that has kept me off the streets, so to speak, for the majority of my scientific career. And I'll try and give you some of the backstory to that and try and introduce some of the people from which I've benefited hugely from their guidance and help over the years. So we're going to start off with the title, The Twist in Light's Tail. What am I really going to talk about? I'm going to talk about the fact that when I shine a laser beam at you, I will now shine it at the President, okay? Not only is she pushed away from me by the pressure of the light, but she's also given a slight twist, and so she might fall over, but let's not hope that that happens. And so I'm going to talk about the stuff that makes you fall over. And so let's start off with hopefully a nice little video. This is a video taken looking down a microscope. We're going to look at some glass beads. And each of those glass beads is 1,000th of a millimeter in diameter, so that's pretty small. It's about the same size as a human cell. And they're moving, if you haven't noticed. They're moving. The music is just a bit of light-hearted relief. The music's not important. What is important, actually, is that I'm shining a laser beam at each of them. And as I move the laser beam, the bead moves with the beam. And so I'm essentially, imagine 8 little laser beams all moving around in some pattern, and I drag the beads with me. Why am I able to do that? I'm able to do that for the same reason I'm able to push Jocelyn away. It's the radiation pressure. And actually, if you want to work out how much force a laser pointer exists on somebody or thing, I take the power in the laser beam and divide it by the speed of light. I could ask for questions now. Cesare, what's the speed of light? Your dad's allowed to whisper, don't worry. Okay, so the speed of light's pretty quick, and the power in this laser beam is actually very small, so it's 3 milliwatts, and so that means that the force it exerts is about a millionth of a newton, or millionth of the weight of an apple. I would need 1,000,000 laser pointers to lift an apple. So it's probably not a very good way of lifting an apple, but it is a good way of moving a cell. Now, that's the linear momentum, but I said I wasn't going to talk about the linear momentum, I was going to talk about the angular momentum. Now, one of the interesting things here is the first person really that I know that sort of raised the question around angular momentum in the way we're going to talk about it today. There'd been papers throughout the early 1900s, but in the 1930s, there was a really important paper written by Charles Darwin. Now, you're probably thinking, hang on a second, I thought Darwin lived before then. He did, but his grandson didn't. So this paper, written by Charles Darwin, is actually written by Charles Darwin's grandson, who was also called Charles. Okay? So Charles Darwin wrote the paper, and I think that's the first paper in the field of what I'm going to talk about for the rest of the evening. And I just sort of introduced that as a sort of little aside. So what am I going to talk about this evening? Well, the story of this evening starts in about 1994. So I had been, this was just coming to the end of my Royal Society of Edinburgh Research Fellowship as it happened. I was about a year and a half into it. And I was really fortunate to have dinner with this man here. His name is Les Allen. And I thought he was, I was, people that know me know I can be a little grumpy, okay, and a little brusque, and I apologize for that. And so he'd come up from the funding council to talk to us about a grant I'd put in to get funded. And it got to dessert, and I thought, I know, I'm going to ask him what his science is, because he just does administration. Anyway, so I said, what is your science, Professor Allen? And he proceeded to tell me about a paper that he had written with his collaborators in Leiden in the Netherlands. And I was so fascinated by his paper that I stopped what I was doing and started doing this instead. And so for the next 10 years at least, I'm very grateful, essentially up until Les's retirement, and even thereafter, we constantly wrote papers, and he guided me through many of those early things, and so I have a lot to thank him for. But anyway, so that's why there's a wine glass there. And he said to me, he said, you know, if you shine a laser beam through the stem of this wine glass, you can introduce a twist to the beam, and that means if you then shine the beam at something, like a nut, you could undo it. And so that got me thinking, and that got me fascinated, and that's where we started. Now, there's going to be a little bit of arm waving now. This is my substitute for mathematics. So I don't know how much all of you know about light, but you're probably familiar with the concept that it's a wave. And if you think about standing on the seashore and the waves are coming towards you, then the waves have a velocity. And you might also appreciate that that light wave carries, or the water wave, sort of would knock something over. It carries momentum. And as we've already established, light waves are just the same. Light waves carry momentum with you. Now, the thing you notice about the water waves is normally when the waves come in, they're sort of one big wide wave. It's all lining up and coming in at the same time, and we would call that a plane wave. And light beams are effectively the same, apart from now I recognize that my light beam is round, and so the wave is everywhere. And so I can think of it almost like as a dinner plate, a series of dinner plates coming towards you. Okay, and that dinner plate is going to push you away. That dinner plate is carrying momentum, it's carrying energy. And that would be the normal shape of a light beam. If I take this laser pointer, I can think of it as lots of little sort of dinner plates in that sense, the wave crests traveling through space. And at the speed of light, pretty quick, and carrying with them momentum and energy. But it's not the only shape possible. Another shape possible is shown on the right-hand side. Now, what I want to try and convey is if I want to work out which direction the push is, I take the plate and I just have a little stick sticking out from the plate, and that's pointing, it's called the pointing vector actually, in the direction of the push. Now you can see, however, if I replace the dinner plates with this sort of spiral ramp, the push, as well as sort of largely along the beam, has also got a twist. And I'll come back and show you some ideas about that earlier. So if I think of the little matchstick sticking out the plane wave, and I'm pushing towards you, move the microphone, and I'm pushing towards you. Now, what I'm going to do is point one of the sticks down a little bit and the other stick up a little bit. And now when I push towards you, you can see that I'm also twisting you. And so it's that distortion of the waves which allows me to essentially impart a twist. Now, I've got one more sort of fairly complicated slide. And so now what I've done is I've animated those waves. So this is the plane wave, the waves crashing on the shore. I thought it was. No, never mind. There we go. The one at the top. The one immediately below that is the one we've just been looking at. But then, as anyone, any lover of pasta will know, one can have more sophisticated spirals than a simple screw thread. If you have a look at your pasta fusilli tonight, all the Italians in the room will know the answer to this. When I look at a pasta fusilli edge on, how many spirals do I see? Any advance? What do we think? Go on, shout it out. The Italians are disagreeing. Well, what can I say? The answer's 3. So actually, it's this one here. That's the past fusili. And so the interesting thing about this twisted light is you can have 1 twist, 2 twists, 3 twists, 4 twists. And the more I twist it, the more poor old Jocelyn is going to get flipped over onto the side because there's more twist in the light beam. Now, this turns out to be extremely important. Why? Well, there's another form of twist in light which people have been familiar with for much longer, actually dating back to Maxwell, whose statue is outside, that we know that light also has a polarization. And in polarized light, the electric field can go around clockwise, or it can go around anti-clockwise. There's not double clockwise or triple clockwise, it's just 2. So when it comes to polarization, it's possible to use light beams to sort of communicate some kind of Morse code message, ... dash. So it could be like clockwise, clockwise, anti-clockwise. I could send a message to you using the polarization, but I can only send a dot and a dash. But now, when I look at these other light beams, well, I've drawn up 1, 2, 3, 4, 5 examples, but actually I could keep going and go +4, +5, +6. I could do any number. So now my light beam isn't just limited to a dot or a dash. It can be an A, a B, a C, a D, an E, an F. And so I can send the message much more efficiently or much quicker. We'll come back to that again later. So now, this is, when I become rich one day, I know it will happen, I'm just not sure when, and I start about home improvements, I'm going to build myself a spiral staircase. But this isn't going to be any spiral staircase. This is going to be a spiral staircase with at least 3 staircases. It's going to be a pasta fusili. Sadly, I don't think anyone's done this. So if someone would like to give me a lot of money for a new house, I will do it for them. But there are examples of double spiral staircases. On the right-hand side, I don't know if anyone knows. Does anyone know where the right-hand picture's taken? Sorry? No. Although I'm interested if that has a double spiral. I tell you something, it's in Italy. It's the Vatican Museum. Okay? It's the old entrance to the Vatican Museum. And the reason why there's 2 staircases, which never meet up, by the way, is that one was the entrance and one was the exit. Okay? And that's so people could go in and out without sort of crossing over each other. Now, on the left-hand side, however, there's another twin spiral staircase. It's from a chateau in France. Does anyone know why there's a tale told about that staircase, by the way? Does anyone know the tale? I will tell them the tale. It is said that they had 2 staircases, so when the wife came home and came up one set of staircases, the mistress could go down the other. I'm sure that's not true, but anyway, and I don't quite know where that leaves my 3 staircases, but let's just leave it there. So an interesting question might be, how do these beams sound fun. I'd like to make one. How can I do that? Well, there's a number of different ways of doing it, but here's just for the physicist maybe, is I can pass a light beam through a block of glass, and if I do that, the light beam slows down. And so if I have a glass block of different thicknesses, I can slow different bits of the light beam down by different amounts. Incidentally, that's how a lens works. A lens is thick in the middle and thin at the edges, so the light beam in the middle gets slowed down more, so my plane wave isn't plane anymore. It curves round. The outside overtakes the inside, and that means now all those matchsticks are pointing to the focus. That's how a lens works. I shape the glass to slow the light beam down and change the shape of the face fronts. Hey, we can do that here too, but now, if I want to make a helical face front, I need to make a block of glass which changes in thickness as you go round. So just in case we can't work out what that looks like, I could do it from having a cake. In fact, I have a picture of a cake, funnily enough, when last year, let's not dwell on why, someone made me a cake that was like that, which was very nice. And what you do is you just say, I'm going to slice my cake up, but each of my slices is going to have a different height. So it's almost like a spiral staircase, just like one one loop of a spiral staircase. And that's what I've tried to show. My drawing skills aren't very good, with that sort of glass object in the middle. It's like a spiral ramp. And when you pass the plane wave through that, out the other end comes this helical shape, so you can make them easily enough. Actually, you can make them even easier than that. I don't know if any of you know what diffraction grating is. Essentially, if I get lots of lines and draw them side by side and then shine light through it, the light beam splits up and one of the light beams sort of zigzags off to one side. If I, instead of having all of the lines straight, I make these lines with a little sort of fork, as you can see here, down on the right-hand side, and now when I shine the light beam through that fork, guess what? I produce one of these funny, twisted light beams. And so they're incredibly easy to make, simply by drawing that sort of Y-shaped pattern on a piece of film and shining your laser pointer through it. And just to say, there's an app for that. It's called iHologram. It was made by a just unbelievably smart research student that I was lucky enough to, I'm going to say mentor. I think he mentored me, actually. So Richard Bowman. And so he, one evening, he decided he'd apply himself, and he wrote a little app so you can download it on the iPhone and make all these funny forked patterns. Now, let's just go back again. That's a picture I hope you recognize on the left-hand side. And we've seen it before, and I've said it, that there's a little matchsticks growing out of the red surface, and one of them's pointing down on one side of the beam, and the other one's pointing up on the other side of the beam. But also I can go all the way around the beam, and I realize there's a whole lot of matchsticks all pointing off at an angle. And that's where I'm telling you the twist comes from. So let us just think about sort of things shooting off at an angle that makes things spin around. And there's the water sprinkler in your garden, not that you've needed it this summer, because it's been coming the other direction, the water, that is. But you know, one of those sprinklers, and all the water shoots out at an angle, and the sprinkler starts spinning round. You could think of that in terms of, in just the same way that the light's energy is coming sort of not just up, but skewed. Now, this is my daughter. Her name is Jenna. Chesney knows her because they go climbing together. And she was 11 yesterday, I should add, and she had an all-day party, and so she's completely exhausted. So her mum and her have stayed at home, which is probably a wise move. Does anyone seen these kind of things you get in the science centre? Okay, you've seen them, where you know these like straws, all, oops-a-daisy, that was not what I wanted to do. Let's just play that again. So you've got a disc at the top, a disc at the bottom, and you connected those two with straight wires. And then I give the disc at the bottom a twist. This is what Jenna's doing for us here. And holding it. Damn, that was not what I wanted. Let's try one more time. Yeah, there we go. And we see this beautiful sort of wicker basket pattern. That is what the energy is doing in our light beams. Okay, it's that twist, and you see it going through the focus in the middle where it's the smallest diameter. Now, I'd like to tell you, if you go into Glasgow Science Centre, that that little sign at the bottom says the orbital angular momentum of light. Despite my best efforts, it doesn't, but it could. So that's the shape we need to remember. Now, I've said that light beams twist. This is the video I've nearly shown about 3 times tonight. This is again looking down the microscope. And you remember before we had that Scottish music dance and we were moving them around because we were making sort of the laser beam move around. Well, here, the laser beam's not moving at all. I'm just holding it still, but the laser beam has a twist and it's making the object spin. And so that actually was work, we'll come to that in a second. That was demonstrated in about 1995, so about 3 years after that original paper of Les and Han and the colleagues in Leiden, which was purely a theoretical paper. It took scientists around about 3 years to come up with some absolutely clear and unequivocal evidence that this twist in light's momentum was real and would make things rotate. And it led to the phrase optical spanner. And essentially, clearly that was not a good phrase, because had I been smart, I would have called it an optical wrench, because Americans don't know what a spanner is. or if they look it up, it cannot always be a good thing. So, so I should have called it an optical wrench, and I would have been more successful, maybe. I don't know. Anyway, so now one of the great things about being in a field at the beginning, and I think it's fair to say, because I was lucky enough to have dinner with Les, I was an early adopter, or whatever the correct terminology would be. But the great thing about being in a field from the start is you get to read all of the fantastic work that other people do, and those wonderful moments, they're wonderful not so much at the time, but in retrospect, when someone publishes a paper and you go, damn, why didn't I think of that? And so there's the papers. I remember Helena Rubinstein Dunlop, lovely lady in Brisbane, as it happens, University of Queensland, who published a fantastic paper in Nature, I think in about 1998. And I went into the lab that afternoon and repeated the experiment. It required nothing that wasn't in my own laboratory. It's just that I didn't have the idea. And so there's been quite a few of those papers, actually, over the years. And so actually that's starting off on the top left-hand there. So Helena, I say a lovely lady, Steve knows her well as well, from Brisbane. Actually, she's Swedish, as it happens, but works in the University of Queensland in Brisbane. A sort of another paper, actually, that you saw come out, and you think, why didn't we do that? Is sort of the use of these beams within quantum optics. Anton Zeilinger in Vienna. So if I move down here, Alan Wilner has just essentially been absolutely breaking state-of-the-art after state-of-the-art in terms of using these beams to encode information, which I mentioned already. How much information can you put on? Essentially a way of making a better communication system. Here we've got a great one here, these laser beams. Normally laser beams are round. Well, not when you put these diffraction gratings in the cavity. They're not. You can make them any shape you like. And this is Andrew Forbes in South Africa. Interestingly, born in Govan, I discovered just recently, but moved to South Africa when he was about 3 years old. And actually a wonderful surfer, as it happens. I didn't know that, but it's amazing what you find out about people. Monika Rischmater in Innsbruck. That's the great thing about science, isn't it? You get all these collaborators in fantastic parts of the world that you can go and visit in the ski season. But, so Monika is, in fact, a fantastic skier, in addition to being a wonderful physicist. She's used these beams in microscopy. And then just to say these things that I spoke about, waves, don't just apply to light beams. Apply to electron beams, apply to sound waves as well. And that's Johann Verbeek, amongst others, moving forward. So, incidentally, you can see how hard my research students work in the top right-hand corner there. I told you Richard was pretty special. That's him at work assembling an optical tweezer, which is the video that you've seen already. There's a story behind that on the top left. I'm not going to go through them all, don't worry. That sort of rather knotted thing. And it's the only time ever that I've been able to cite Lord Kelvin in a paper. And so Kelvin, as the President was telling us earlier, Kelvin did many, many, many wondrous things, some not so turned out correct things as well. And one of his great ideas was that he understood atoms and molecules were not in the ether. Slight problem that there turned out not to be an ether. But it was a good effort. And actually, if I understood it better, I often ask myself, how similar to string theory is it? But anyway, and he had this idea, and he gave up on it in the end, not because of the ether. It predated disproof of the ether. He gave up because he couldn't work out the mathematical formalism to get the stable knots as a vortex field. And that was a problem that Mark Dennis, who I was very proud to lecture to as an undergraduate, and he told me how dull my lectures were afterwards, but that was kind of him not to tell me at the time. But since we actually had a fantastic collaboration together. He's a very powerful mathematician, and he was able to sort of work out the maths behind these stable vortex knots, which was the problem that had actually stumped Lord Kelvin. And then using our light beams, we were able to recreate not the ether, I stress, not the atoms and molecules, but the mathematical construct associated with that. And so now I'm just going to talk a little bit for a few minutes about some work that Mark did with myself. And so that's a picture of Mark at the bottom. He did his PhD with Michael Berry, that some of you may know, down at the University of Bristol. And Mark and Michael are both still there. And if anyone knows Mark at all, you'll know that I always get told by everybody else at Bristol, we know exactly what you and Mark are doing, because when you ring him up, Mark has an incredibly loud voice. And so whenever Mark's on a telephone conversation with everybody, the rest of the floor will know exactly what's being planned. So I go down there and go, oh, no, I know exactly what you and Mark are doing. I heard him on the phone yesterday. So anyway, but he's a super guy. Anyway, and now this twisted light, I think you think like, oh, it's something you have to do with spiral phase plates or with funny forked holograms. And actually, no, it's all around us. So if anyone has ever looked at a laser beam sort of projected onto the wall, and let's say it's a green laser beam, you don't see a big green blob. You see a big green blob with lots of little black specks in it. And those black specks we call optical speckle. Now, so that's what this next picture's trying to show. That's like, imagine this is the light you see. I've drawn it white here, not green, but that's the intensity of the light you see backscattered from the wall. If I could see phase, this is what I would see. Now, that's a bit of a strange diagram there. The phase of the light at every point is some value between 0 and 2 pi. And so the different color there represents the different phase. And you can see there's some very special places. The special places where all the colors meet. So what's the phase? The same problem is, what's the time at the North Pole? You're probably wishing you were there just now. But what's the time at the North Pole now? It's 20 to 7 here. What's the time at the North Pole? All the time zones meet. I suspect there's some international convention for time at the North Pole, but let's pretend we don't know what it is. So time is ill-defined at the North Pole and the South Pole. Let's not be Polist about it. Either is correct. The time at the North and South Pole is ill-defined. And it's the same with the phase here. The light beam has no phase at those points, which I'm going to mark. Why have I marked some of them red and some of them green? Depends whether the colors go round clockwise or anti-clockwise. It depends whether those matchsticks are twisting to the left or twisting to the right. Actually, those positions of phase singularity, as they are called, luckily, have no intensity. Those positions of phase singularity are the little black dots we saw in the big green beam as it bounced off the wall. They're not black by accident. They're black because the phase is singular. There is no intensity. Absolutely no. Classically, okay, we can now get into quantum fluctuations. Classically, the light there is 0 intensity. Now, if I now pick up the screen and start moving it towards you, so these are the little black dots marking the blackness. You can see the phase. I plotted the phase. And if I move the screen towards you, you'll see those little black dots move around. And sometimes 2 black dots come together and disappear. Sometimes 2 black dots just appear out of nothing and move apart and then come together again later. Now, as I do this, moving the screen backwards and forwards, it's almost like taking one of these medical x-rays that sections through the body. Apart from now, I'm sectioning through the light field. And you realize these black dots aren't black dots at all. They're actually black lines. They're black lines weaving like, let's go back to the pasta analogy, like spaghetti, just twisting and turning. Apart from every now and again, 2 of those black lines come together. So it's not like spaghetti at all. It's like a spaghetti hoop. Okay, and you've moved the screen, and you've seen the back of the hoop. That's where the 2 black lines appear. And then the 2 black lines come together, and you keep on moving the screen, and then you see the front of the loop, where they're joined back together again. And so these lines of darkness around which the energy is circulating are absolutely intrinsic to every light field you have ever seen, other than perhaps a perfect laser beam, ironically. All the light we see around us is riddled with these little lines of darkness. And this is now this is real experimental data. It's from a paper that Mark and I and Kevin and Florian wrote together back in 2000. It was one of my ref papers, for what it's worth. That's a bit of an inacademic joke. I can see no one's going to get that. It was a ref paper. And it's the paper that has the title of which I am proudest, which is why I included it, The Fractality of Light Darkness. Because it turns out that these random lines are, in fact, Brownian statistics. So it is essentially that. Now, I'm going to skip over this little bit. Sorry, Steve, that was a bit where I was going to talk about something that you and... There's more of that to come. You'll get that in a second. So I just wanted to reflect here. This is a picture that's, many of you know, that's Graham Gibson and Johannes Kortiel, two people that I've had the pleasure of working with for many, many years. This is actually 10 years old. It's 2004. It was, again, as a little academic joke, it's the highest cited paper I have. I submitted it to FISREV Letters, and it was rejected by the editor before review. So I don't quite know what that tells you about me or the editor. It's a lottery. I think that's probably what it tells you. Anyway, so this is the first paper which tried to use these beams to communicate. Said, let's break out of dot and dash, and let's get into using the alphabet. I thought it was a pretty good paper. Anyway, so it came out, and that was fine, and it engaged quite a lot of people, including New Scientist, which is fine, of course, and it was a delight to work with New Scientist on promoting it, and nice little picture of the helical wave coming in, clearly a laser safety issue there as it hits the guy in the head. But anyway, leaving that aside, anyway, you see it at the top there, I don't know if you can read it, twisted light. It's fast, it's furious, and perfect for talking to aliens. I wasn't sure who the alien was, but if you open the magazine, oh my goodness gracious me, it was me. Right, okay, so not a great advert for laser safety either. I would never dream of doing that now and setting such a bad example. The light was, of course, at an eye-safe power level, just for the avoiding of doubt. So, moving on, and this is the last little bit of my talk. So this is work which it's a delight. You'll hear from Steve shortly, so you can see Steve's smiling face there, and Fiona as well, Steve works with, and as I'm sure you both know, all know rather, that they're essentially the theoreticians, okay, so they're very good at mathematics and things, amongst everything else, but and also a picture there, Martin Lavery, delighted to say one of my own research students, who, let's talk about the opportunities that the UK gives to young early career scientists, has a research fellowship, not from the Royal Society of Edinburgh, as it turns out, but from the Royal Academy of Engineering, who also offer these things, and so he's just started that. And in fact, he's just come back. You remember I mentioned Alan Wilner in the University of Southern California. So Martin, essentially after finishing his PhD with me, got this fellowship and spent the first year of that out with Alan, essentially getting experience of an overseas working environment, and indeed published tons and tons of papers while he was out there, which is fantastic. So that's Martin. Now, so this is, I'm going to talk about experiment and theory that we did together hand in hand, Steve's group and my group, and we published this at the beginning of last year. So the Doppler shift. I don't know how many people are familiar with the Doppler shift. I suspect most of us are orally, even if we're not scientifically. When that police car comes zooming towards you and zooms past, I won't do an impersonation, but you get the change in pitch as it comes past, or whatever, other way around. You know, and it's called the Doppler shift. If I ran towards you with this green laser pointer very, very quickly, Usain Bolt style, it would look blue. If I ran away from you, it would look red. And of course, Jocelyn herself would tell you all kinds of things, how that Doppler shift is pivotal to understanding many things about the universe around us in terms of working out how far away distant objects are. It's not the only way you can do it, but it's a very natural way to do it. And so the Doppler shift is always associated with objects moving towards you or running away from you, or usually. Now, that shift in the color of the light beam has to be accompanied by a change in its energy, because the energy that every photon carries scales with the wavelength, with the frequency. So blue photons have more energy than red photons. Where did that? I can't just generate energy out of nothing. I have to do work to generate energy. Where's the force? What work am I acting on? Well, we already know the answer to that question. If I point a laser pointer at someone, it's pushing you away. So if you run towards me, you're doing work against that force. Where does that energy go? Actually, it goes into the light beam, and the light beam, scattered from you, changes color. Now, that's quite an unusual way of seeing the Doppler shift in terms of acting against the work, but it's actually mathematically correct. If you just go through those numbers, you'll get exactly the normal expression for the Doppler shift. Well, let's just take that one step further. I've also said that the light beam puts a twist on you. And if I sort of rotate myself against the twist, I'm doing work on the light beam. So where does the energy go? Can I shift the light beam, not by running towards you, but simply by sort of doing a dad dance, as my daughter would say, which normally has my hands down here rather than up here, but anyway. So twisting around surely should shift the light beam, and that was a sort of thought that we had for quite a while. I should say that we spent a year trying to do the wrong experiment and saw no effect, okay? And because we didn't understand what we were doing. And then you have one of those sort of moments in the shower moments, or out on a bike, as is more common with me. And you go, no, that's wrong. It should be different. We're doing the wrong experiment. So what we tried to do was a different experiment. It turned out to be the right experiment, whereby we shone a light beam at a spinning disk. The disk is not coming towards you. It's not moving away from you. It's simply rotating. You know, one of those boards that you're probably wishing you could tie me to, where you spin me around and throw daggers at like a circus act. So it's like one of those sort of, big boards. Apart from this wheel was about so big, and it was, in the first instance, actually, we connected it up to a little electric motor that we got from a radio-controlled car. Why? Because people that race radio-controlled cars have a real interest in making electric motors that go really fast. Okay? So and the wires to it, incidentally, were like, quite a quarter-inch thick. It was a heavy-duty thing, and this thing went the proverbial off a shovel. It was fast. Turned out we didn't need it to go that fast, but we didn't know that at the time. And so we span the disk and looked at the shift in the frequency of the back-reflected light. And so long as we only used twisted light to do that, we could see a frequency shift. If there was no twist in the light, there's no torque on the object, and there's no frequency shift. As soon as you twist the light, there's now a torque on the object, and when you spin the object, you're doing work against the torque. There's a frequency shift. If you double twist the light, guess what? You're doing twice the work, and you get twice the frequency shift. So the pasta fusilli, with its 3 twists, gave 3 times the frequency shift as the screw thread, or whatever. You turn the sense from right-handed to left-hand, instead of being shifted up, it shifted down. So all of those things worked in exactly the way that we thought they might do, and Steve and co helped us. Well, we all sort of sat down together and worked this out. And there's all kinds of subtleties about it, which relate to why you don't bang your head when you walk up spiral staircases, but let's leave that for a moment. Actually, you tend to bang your head when you walk up. It's when you come down, it's okay. But anyway, so that is the end of my slides. I just want to say that this twist in light's beam, of course, has been extremely important to me, and I've had years of fun and hopefully some use for everybody out of it as well. But I think it's also changed the way that people think a little bit about light beams. And, you know, this is one example of a shaped light beam. Actually, you knew another example. It was a lens. I mean, in retrospect, it seems pretty obvious, you know. Oh, you shape the light beam, and guess what? It changes shape when it propagates. A lens focuses it. But then just to realize that, you know, doesn't have to be a lens. It can be a spiral faceplate. It can be a sort of wavy thing which produces something called an airy beam. Let's not go on those properties. But there's now a whole family of light beams which do special, sometimes useful things as they propagate. And I think that's all come about this general realization that it's not just about the intensity, it's about the phase too. And that phase shaping shapes a light beam. And, you know, you bring that through to better communication systems, better sensing systems, and indeed better imaging systems. And that it's pretty much where imaging is pretty much now where my own focus lies through the quantum hub that we have set up here in Glasgow. So with that, it merely falls now for me to thank, in a sort of one of those nice ways, the people that have had the enjoyment of the journey through physics. In particular, I'd like to thank Sonja Franke-Arnold and Johannes Kortiel, who are sort of academics that essentially have to put up with being in the next office to me and listening to the other end of the conversation with Mark Dennis, because I also have a bit of a loud telephone voice. But also, and I can't stress this enough, the real excitement that I have had from my academic career to date, and I'm only 52, as I mentioned, so I hope I still have a few more years left. It's just the wonderful experience of working with basically research students. I never tire of the new research students coming into the group, and they start off and you're sort of nicely telling them what to do, and by the time they finish, actually that they're telling you how it works, and you learn so much back from them. And that's not all of them by any means, but I just thought I'd like to flag up some names there. You've heard about Richard already. Graham, that was my research student, Graham Gibson, you saw a picture earlier that went on. Somehow I've managed to keep hold of him all these years to make our experiments work, etc. So, well, with that, thank you very much. I hope you found it interesting to hear a little bit about our work on twisted light beams. I'm very happy. I don't know whether I'm allowed to take any questions now. President's nodding. I'm allowed to take some questions. Is there a mic or anything for people to ask questions, or did they just go for the shouting option? Okay.
Thank you very much. And there are indeed microphones, so if you want to ask a question, raise a hand and we'll get a microphone to you. Let's start here, please. And then we go to one.
What was the experiment you did on the Doppler wavefront, which didn't work?
That's a good question. So I thought we would generate twist. So I thought if we shone a plane wave at the rotating disk, the scattered light would have a twist in it, that it would pick up momentum from the spinning disk. Turns out it doesn't. It just shifts the frequency. So it changes the color. So if I have to use twisted light, okay, so that was the experiment we tried. I thought we were going to change the twist in the light beam by bouncing light off the disk. We don't. That's the experiment poor old Martin got lumbered with for a year.
You talked exclusively about light in terms of waves, but of course we know that it has a particle ontology as well, i.e. it has a wave-particle duality. How do you screen the particle aspect of it out so that you get unbiased results?
Use a lot of particles. Is the easy thing to say. So I should say that it's quite interesting actually, because when Les and his co-workers in 1992 wrote their paper, it was really presented as a wave phenomena And because of that, many people, like myself, got sort of hung up that it was somehow a many photon property. As in, I said, use a lot of particles and it all sort of works out. Now, actually, of course, when you look at the original paper by Darwin, of grandson fame, actually that wasn't considered for waves at all. That was considered for quantized interaction. Actually, his argument was, in the Darwin paper, when an atom normally decays, it's a dipole transition, and that means that the quanta of light, let's in modern language call it a photon, although it's not the language that he used in the 1930s, let's call it the photon carries away from the scene of the crime h-bar angular momentum. Everyone goes, yeah, that's how it works. And Darwin pointed out and asked the question, well, what happens when it's a quadrupole transition? There's 2 units of h-bar. What's going on? So it was that paper by Darwin which said there is more to light's twist than just the polarization. And so essentially that paper recognized the quantized nature, I mean, not in any profound, well, I think it's actually an amazing paper of the time. And so actually the first experiments deliberately using this extra twist were those, I put them up on the screen, I mentioned Anton Zeilinger. He was then working in Innsbruck, now works in Vienna. And he essentially did a series of experiments showing that this property of light's twist applied not just to many photons, but to individual photons. And indeed, the work I didn't show with Steve and I was building upon that work of Anton's, establishing, if any of you within quantum mechanics know of the EPR paradox, the Einstein-Podolsky-Rosen paradox, which Einstein originally formulated for position and linear momentum. Essentially, we recast that in terms of angular position and angular momentum, and then did the experiments to show that there was an angular equivalent to the EPR paradox, again, applied at the single photon level. So it's a very good question that you raised. This twist of light is both a macroscopic quantity, in that you can make things rotate that you can see. It is also a microscopic or atomic quantity in its interaction with atoms and molecules, or indeed as a quantum parameter in some kind of quantum communication system.
I may have got this wrong, but most of the twist in light that you described seemed to come from a laser or some other artificial source. The light coming from the sun, does it have a twist property in it?
Well, actually, in the same way that light scattered from a surface has twist, then any random light field has twist and twirl associated with it. It averages, for a normal light field, it effectively time averages to 0, and space time averages to 0. So if you put something out in sunlight, don't expect it to start rotating anytime soon. Now, if I then take that sunlight, close the curtains, put a small hole in the curtain to let a small beam of sunlight come in, and then pass that beam of sunlight through my spiral faceplate, then I can introduce a twist to sunlight. So sunlight is not immune to having a twist imparted to it. And indeed, we've done experiments with intense white light sources to show that we can, in fact, make objects rotate with white light. So it's not special in that sense that it's monochromatic. If you want a clearly defined twist, it needs to be what people call spatially coherent. And that means that if it's a normal light source, you have to pass it through a pinhole first. And that means you don't get very much light, because not much light comes through the pinhole. But in principle, there's no reason why we couldn't start off with a tungsten bulb or any other light source for that matter. So it's not peculiarly a laser property, though it is easier to see if you're using a laser.
Thank you. As we gain more information about light and its makeup and the implications of twists, what practical applications do you think we're on the horizon of seeing over the coming immediate period?
So if I get a sad view now into the mind of a scientist. One thing that sad people like myself do is that we check out every week which other scientists have referred to our work. Okay, and partly that's ego, but it's also genuine interest to see what people are doing, because hey, maybe there's an idea that one can build on there. And so if I don't do this every week, of course. He does, it's true. I would find absolutely, without doubt, the thing that interests the international community in these beams at the moment is the prospect of using them in communication systems. It's going from ... to A, B, C, D, F, A, B, C, D, Y, or whatever. It's the ability to maybe, and there's, I don't want to oversell it or overhype it. Turns out there's no such thing as a free lunch in physics, usually, unless you believe in squeezing. But normally there's no such thing as a free lunch. So there are problems with, you have to make sure the system's better aligned, your lenses need to be bigger. But if you accept that, then you can actually put more information on a light beam. And that is what the citation record literature would show is happening. So it's the communication angle. Pardon the pun on angle, but never mind. Yeah. So that's, communication technologies.
Further questions? Yes, sir.
Miles, has anyone then done this and put it down a fibre yet? And
Well, that's an interesting question. So if people have put it down a fibre a little, it turns out you need a big fibre. Because I don't know if you remember seeing those images, probably saw that as the L goes up, the more twist, the beam gets bigger. And so actually, if you take a normal telecoms fibre, it's called a single mode fibre. And that's done that deliberately, so the different modes don't travel down at different speeds and confuse the message. But if it's a single mode fibre, the only beam I can put in is the zero twist beam. Now you can sort of defeat that a little bit by going to a shorter wavelength. And if you go to a shorter wavelength, you discover in the same fibre you can put zero twist and one twist. And if you're really careful about it, they don't get confused. But then that's only giving you a factor of 2. So if you really want to exploit this down fibre, you need special fibres. And there's a number of American groups, incidentally, doing exactly that, and indeed German groups as well, saying, can we make special fibre? But if you're going to make special fibre, you're left with, well, why don't I just put down 2 normal fibres or 3 normal fibres? And actually, the size scaling may be not that bad. And so there's competing technologies there. Some of them are called photonic lanterns. There's a whole, but I think what's interesting is whether it ultimately turns out that light's twist is the solution. Certainly the interest that's been generated by light's twist in doing things like this is that people are now considering all different kinds of solution. So I think in all likelihood it will turn out that light's twist may not be the ultimate answer, but it probably was what started people asking the question. And so often in science, actually, I think, dare I say, profound moment, it's the question that's difficult to, it's asking the right question. If you can ask the right question, then finding the answer is sometimes extremely difficult, of course, but it's actually about identifying the question. So the question that you want to ask, Alistair, is how can I get more information down my fibre? That's a good question. Can I use the shape of the light beam to do that? That's a good question. Well, sorry, I mean, they're all good questions, but you know what I mean. So yeah, people have tried, they've done it to some extent. Watch the space. Buy shares now. No, just kidding.
Your work has been in optics, but it seems to me likely that a lot of this will apply to electromagnetics in general. I'm aware of some experiments that took place in Venice using communication Wi-Fi. But is there anybody else who's working in, say, the microwave region?
So we've done some microwave work ourselves, actually. Back in the late 90s, we made beams at 90 gig, which is 3 millimeters, where the phase plates are sort of physical things you can sort of pick up and machine on a milling machine. So yes, I mentioned, so people have done it for electron beams. And actually, electron beams, when I first saw it, I went, yeah, electron beams, big deal. Electron beams are special. Because think about it. We've said that the energy in these beams is sort of, Steve, look away, spiraling down the axis. And you go, fine. Hey, that's an electron. What happens when an electron spirals through space? Does anyone know? An electron spiraling through space like a coil, hint, hint, hint. A coil of current going round and round and round. What happens? Magnetic field. You generate a magnetic field. So the fascinating thing about these electron beams is as the electron beam comes towards you, when you give it a twist, it generates a magnetic field. Not sideways like most EM field, but along the beam axis. And so that gives people a new way of probing magnetic domains and the way they work within hard disk data storage and the like. And so the interest the electron microscope community has is for their studies of thin film magnetism, because you can probe the thin film material with a B field that's coming straight down into, not oscillating, it's DC. Okay? And so you go, wow, this is a new form of electron microscopy, which I think is really, really exciting. And there's a number of people working in this area in the UK, America, Netherlands. First paper was a Japanese paper, actually, as well. So there's that. There's people like Ian McNulty in Argonne, and I've got a synchrotron there. Synchrotron's one of these funny machines where electrons go round and round and round very fast in a circle, and every now and again they come past some magnets and they wiggle, literally up and down, North Pole, South Pole, attract, repel, and in doing so they give out light. So these wiggling electrons give out light, and it's how people make soft X-ray lasers. And he has started twisting these beams. Why would you want to do that? Well, it turns out that one of the big things that people do with synchrotrons, and in fact their financial justification, comes from doing X-ray crystallography of proteins. And actually it's really difficult to know protein structure, and you do X-ray crystallography on the protein that you desperately try to crystallize or whatever. But the difficulty, and this now comes back to a subject that Steve's interested in, it's very difficult to tell clockwise proteins apart from anti-clockwise proteins. They look the same. And that leads to all kinds of problems in drug discovery. And so if you now probe that with a twisted beam, you break the degeneracy between right and left, and the diffraction patterns look different. And so that's Ian's motivation of doing helically phased soft X-rays. And then there's also stuff on using it for acoustic waves. In fact, one of the, I didn't show you the video, I could have done. Start off with a ring of loudspeakers. Let's have 8 of them. Let's have them all at the same frequency. You hear a noise. I can now change the phase. So each loudspeaker has a different phase, and I generate a beam that sounds the same, it has the same frequency, but it's helical. And so actually, sound waves can't be circularly polarized, not in air, because they're longitudinal waves, but they can carry angular momentum still. They can carry it through the twist. You're thinking, oh, well, okay, big deal. What's that going to make a difference to? Now, you remember how I said at the beginning that the force in a light beam was the power divided by the speed. So, do sound waves travel faster or slower than light? Okay, they travel about 1 million times more slowly, and therefore they carry, for the same power, 1 million times more twist. And so actually, with a sound wave, it turns out you can spin a dinner plate. There's probably easier ways of spinning a dinner plate, but you know, and yet, believe me, you sit there with the ear protectors on, but you can spin a dinner plate with a sound wave. So there's different, it's not just blue light that it works for.
Question right at the back.
With light, the torque is very small, but applied on a long time, it can have a microscopic effect, I guess. So could that be useful, for instance, to help on the positioning, rotational positioning of satellites when, well, it could help reduce the weight of the satellites or help when the rotating wheels are broken?
So it's an interesting, so the question is, could I use a light beam to rotate a satellite? Well, clearly I can exert a torque on a satellite, and in fact people have thought about using these light beams for communication, because it turns out, you know, how I said they're very sensitive to alignment. If I want this communication system, I have to be careful with alignment. Well, in some ways that's good, because if I'm shining a light beam to you and Steve's trying to listen in secretly to my message, he can't, because he's sitting in the wrong place. So then actually there's some interesting sort of security implications to using light beams. But the amount of torque I'm going to exert is extremely small, realistically. So I said in order to levitate an apple, I needed 1 million laser pointers. I suspect if I point 1 million laser pointers at an apple, the apple's not going to be there for very long. Not because it's levitated, but because I've made it rather hot. And so the interesting thing about scaling laws, of course, is when something gets 10 times smaller, it gets 1,000 times easier to lift. Okay? When something gets 10 times smaller, it gets 100,000 times easier to spin, because the moment of inertia goes with the 5th power of the radius of the sphere. And so this is one of the, so making it small really helps. You know, even a factor of 10 makes it 100,000 times easier to spin. So yes, I can spin something a few microns across quite quickly, but if I now make it 1 meter across, that's 10 to the 30 times harder. That's going to be difficult. And again, the laser power would be so high. Sounds a fun experiment, though.
Indeed. Can I invite Professor Steve Barnett to come and give the vote of thanks?
Not sure where I'm meant to stand now.
Well, I'll stand here if I may, so I can use the microphone. So, like most of you, I've always liked my novels with a bit of a twist. I like my cocktails with a bit of a twist too. Perhaps you'll understand after this evening why, for, 20 years working with this man, I've also liked my light with a twist. All those years ago, it was, as things start in science, it was an intellectual curiosity. There were half a dozen of us who thought this was fun. And in very large part due to Miles's leadership, but also to his remarkable communication skills and galvanizing a community, we've come to a position where the field is not just large within physics, doesn't just cover all these fields, but it's now pulling in elements of engineering and in chemistry and other fields as well, due entirely to this remarkable man and his communication skills. So I invite you, if you would, to join me in thanking him again for his excellent lecture.